Hi, I'm Laura Merriman, an assistant professor in the Biological and Agricultural Engineering Department, and I'm here to talk about the Engineering Grand Challenge of providing access to clean water. Most of the time when you think about this, you actually think about like some sort of treatment plant, like whether it's a drinking water plant, wastewater treatment plant, or some sort of mechanical, physical process that's happening. There's actually a lot more to it than that. Biological and agricultural engineers are instrumental in helping increase the water quality that's actually going into a lot of our water resources, whether it's streams or wetlands or lakes. We try to improve that water quality so one, we have a better habitat and biological ecosystem in that area, but two, the water treatment plants spend less money actually treating that water. The cleaner it is going in, the less money they have to actually spend to get it treated down to drinking water standards. Biological and agricultural engineers are also very instrumental after water leaves a reservoir, lake, wetland, stream, in that we try to conserve water. We do a lot of research on irrigation efficiency, stormwater management, water quantity issues. One of the big problems is we don't usually have water when we need it and where we need it. So some areas of the state might need a lot of water for irrigation purposes, but some areas might be flooded. So we prepare engineers and do research in our department to help put water where we actually need it, when we need it. Biological and agricultural engineers also work in many different ecosystems. Think of a traditional agricultural engineering looking at a crop or an agricultural field. We could also look at wetland systems, whether it's stormwater or natural wetlands. We look at streams, whether they're natural streams or we might have to restore some of this stream. One other great thing is we also get to work at a lot of different scales. So maybe we're just focusing on 100-foot length of a stream or a really small constructed wetland that you might see on Centennial campus. Or we could blow that up and actually look at an entire Neuse River watershed, or a 25-acre wetlands project that's down in New Bern, or the natural wetlands we have on the coast. We could even look at Lake Johnson, which I'm here in right now, which is a smaller lake, compared to Lake Jordan, which is a bigger lake with different beneficial uses such as drinking water. But then we can even blow that up even further and actually look at things on a whole state level, doing all kinds of data analytics and modeling with all the data we've collected over the years. It's time to actually start analyzing those data and providing management decisions to the state of North Carolina or the city of Raleigh. We get to work with many different ecosystems at many different scales. Precipitation, such as rain, sleet, snow, is really the beginning of the hydrologic cycle. In North Carolina, we're mainly dealing with rainfall. So that's where our whole providing clean water grand challenge begins, is with rainfall. We spend a lot of time collecting data on rainfall, but more importantly, we use rainfall data that other people, such as meteorologists, have actually collected for us. And we use this rainfall data to calculate and estimate runoff in our areas, whether that's stormwater runoff from like an agricultural field, an urban environment like where I am now, or a golf course, any type of environment, you're going to have runoff associated with that. This runoff affects our streams, affects our ag production, affects lakes, and different types of water quantity in our environments. So the thing with rainfall is usually we either have too much or we have too little. So it depends on the time of year, or it also depends on the area of the country. So I worked in Southern California, where water conservation is very important because they just don't get a lot of rainfall. They might get 6 to 10 inches of rain a year. But here in Raleigh, especially on the coastal plain, you might have issues where you have too much rainfall, and that's where flooding occurs, where we get maybe 50 inches of rain a year. So it's important to have practices in place where we can actually capture water during a storm and use it later. When you typically think of biological engineers, the first things that might come to your head are streams, wetlands, lakes, anything with greenery or some sort of biological habitat. But that's not necessarily true. We actually work in urban environments too. So I am at the Colonnade Center in North Raleigh, and this is a really unique stormwater project. The city of Raleigh decided to help develop this area, but land prices were really expensive. We're also in the Falls Lake watershed, which has very high environmental standards and conditions that must be met for stormwater. They got pretty unique here They didn't want to sacrifice any parking, so they actually installed some underground infiltration systems below my feet. So all of the stormwater runoff from this parking lot flows to these tanks underground. These tanks and these pipes, as you can see from this photo, have holes in them. So all of that water will sit there and slowly infiltrate into the groundwater below, recharging our groundwater system, but without sacrificing any of the important parking real estate that we have in this area. This is a cistern that is connected to the Whole Foods as part of the same project, and they actually collect stormwater runoff from the roof of the building, so it's piped through the gutter system into this giant cistern, and this water is used for toilet flushing in the store. And as you can see from this sign, on an annual basis, they save around 340,000 gallons a year of water. So it's really important as biological engineers to think about conserving water resources that we might not have later. So they're able to actually save a lot of water by using rainwater harvesting at this facility.
My name is Matthew Jones. Finished my undergrad with BAE in 2005 and my PhD in 2008. I'm a senior associate with Hazen & Sawyer. I lead our stormwater practice group, and a lot of my work ties to green infrastructure, working with municipalities throughout the country, especially along the East Coast and some of the larger cities like Boston, New York, Philadelphia, and Washington, D.C., on how they can integrate green infrastructure and more natural practices as part of their stormwater management efforts. Our firm does all aspects of water resources engineering, so even integration with stormwater as it affects water supplies or how it interacts with wastewater treatment and nutrient trading, really across that spectrum. One of the things I think is great about this department is you're able to be exposed to a lot of hands-on technology, working with technology, solving different problems, a lot of those things that I think will directly benefit later in your career. In my job now, where I can talk with municipal clients of a wide range of technical backgrounds about what are the challenges they're dealing with and what kind of solutions we can use, many of those relying upon biological systems that are a focus in this department. One of the things that's been most exciting to me is working with green infrastructure in these ultra-urban areas, and I'm fortunate in that to be doing that at a number of different places. Recently one example is in Boston, where they're exploring how they could use green infrastructure, different configurations of bioretention, impermeable pavement, things of that nature, to help achieve their stormwater management goals. And so they're at the pretty early stages of that, so it's really exciting to plug in and evaluate how that could work in terms of an implementation standpoint, how those are going to be built, but even in terms of how you're going to design and where you're going to put those facilities and who all is going to need to be involved in that coordination and that planning and that design. I think a lot of that ties to my experience here in this department, being hands-on, working with those practices and being able to give a realistic representation of what some of those things are going to look like, what are the challenges that they're going to face, and how they can navigate that process.
I'm an assistant professor in the Department of Biological and Agricultural Engineering here at NC State. My research program basically focuses on the transport of water, contaminants, and sediment through waterways and floodplains. So we deal with all of the problems that are governed by the dynamics of water, sediment transport, and then the morphological evolution of the channel bed. Right now we are in Rocky Branch. This is a restored stream within the campus of NC State. We have a project with the Department of Mitigation Services that basically we're looking to develop a process-based framework to guide the design of new stream restoration projects. For that, we're going to apply numerical modeling of several streams, and we're also going to do field monitoring campaigns to actually determine the erodibility parameters of the bank and then the properties of the channel bed. So basically, the processes that we are going to be looking at are very dynamic, and then changes in the bed will change the characteristics of the flow field, and then those changes in the flow field will change again what is happening in the bed. So it's a constant and dynamic adaptation to external drivers such as hydrologic events or dams or different man-made structures that can be placed along the stream. This is the jet erosion test that is basically used to determine erodibility coefficients of stream banks. So the jet erosion tests basically have two important parts. One is the head tank with a constant pressure. It was developed by the USDA Agricultural Research Service, and basically what it does is that it will jet the water and then this jet will be progressively scour the surface of the bank. And then we are going to record the temporal evolution of that scour. So by getting different scour depths at different times, we can then fit that relationship and then determine a mobility coefficient, which is basically related to the texture of the bank material. And then we're also going to determine the critical shear stress, or the maximum force that you need to apply to actually cause some sediment. So we look to understand and develop better tools to predict stream bank erosion failure. So stream banks, they are a major contributor to both sediment load to streams and then phosphorus to streams, which basically impair water quality in downstream water bodies. So by having better tools to actually design the streams and mitigate the impacts of stream bank erosion and failure, we can improve water quality in downstream reaches of water bodies. So the main challenge in stream restoration is that there are not two streams that are the same. So the heterogeneity that you will find both in the channel bed materials and in the banks is an important factor, because they will actually control all of the processes that are happening within the channel. So you will have channels with very coarse material, as you see in Rocky Branch, or you will have sandbed systems where the material is very mobile and they will be transported downstream relatively easily. So the important thing, or the biggest challenge, is to actually use the fundamental knowledge that you will get in your academic formation to actually go and apply those tools to different characteristics. So one amazing thing about the Biological and Agricultural Engineering Department here at NC State is that we actually work in the field. So we try to understand the system from within. We come to the field, we take different, for instance, sediment samples to characterize the bed material, we try to characterize the bank, and we try to understand how this system works by actually measuring and applying in situ techniques to characterize it. It's not only that, we also have numerical tools that actually help us to predict what will be the behavior of this particular system when, for instance, it is subjected to an extreme event like a tornado. If you are able to understand the system during normal flow conditions, you actually can help prediction tools to understand what will happen in the future.
My name is Natalie Nelson. I'm an assistant professor in the Biological and Agricultural Engineering Department here at NC State. And I'm also the principal investigator of the Biosystems Analytics Lab, which is a research group that investigates questions related to biological and natural resources management, but mostly using computational approaches. I'm using these tools within my own program to study issues related to land-sea connectivity, so identifying how inland management practices can ultimately lead to coastal consequences like changes in water quality. Part of the research that my students and I are carrying out has to do with understanding how estuarine water quality might change under different scenarios. So scenarios being climate change or different land use change, and also trying to consider how sea level rise might lead to changes in water quality by altering the salinity patterns that we have in freshwater and estuarine systems. Because once you change the salinity of a system, often there are different types of species that can no longer live there because they have pretty specific salinity thresholds. And so we're trying to understand how all of these different changes that are occurring at the same time, like changes in precipitation, changes in extreme events, changes in sea level, how are they ultimately leading to different types of ecological interactions, and how can we try to mitigate some of those impacts? So in Florida in particular, but also in states across the country, we're seeing a lot of issues now with algal blooms in coastal waterways. And in some cases, the causes of these blooms is fairly straightforward. But there are other situations in which the causes of the blooms seem to be due to some sort of human manipulation of the water management in a system. So in particular, in this one system in South Florida, we're studying how discharges of water, so there's a large lake in the center of the state that they will control the water level of to prevent flooding. They'll release water to the coast once that lake is starting to approach a level that could threaten flooding in some of the downstream areas. And when they release those waters to the coast, we think that they're actually instigating algal blooms in some cases. So by delivering water that has a lot of nutrients in it, such as nitrogen and phosphorus, we think that these types of pulses of water are leading to changes in the ecology of coastal systems. So when it comes to water quality and water quantity, I would say in the past, engineers have often been trying to overcome the forces of nature. So we're trying to create systems that will battle directly against the way a system might naturally trend towards. And I would say that now, in particular with biological and agricultural engineering, we're embracing natural solutions, so trying to understand how can we use our understanding of both engineering principles, but also the biology and the ecology and agronomy of these different systems to actually design engineered systems that integrate well with the environment. Because what we're finding is that often when you try to fight against the forces of nature, you fail spectacularly. And so if we can actually come up with strategies that allow for us to have systems that are engineered but also well received by the environment, we're more likely to have higher resiliency to different types of future change. So I think that biological and agricultural engineering is uniquely positioned to really address some of these grand challenges related to natural resources management because of the way that we're embracing both the biology and the engineering principles of these systems. So one thing that's unique about biological and agricultural engineering is that we're taking aspects of other core engineering disciplines like mechanical engineering, electrical engineering, civil engineering, but we're putting them in the context of managing natural resources and addressing grand challenges related to providing humanity with food, water, fiber, and energy. And in particular, we have a really strong focus on sustainability in this department. So how do we use resources more sustainability while still using principles from these different facets of engineering like mechanical, electrical, and civil. But we're putting them in a really applied context and in a way that we're directly addressing many of the challenges of today and tomorrow.
Hi, I'm Shelley Sadie. I'm assistant professor in biological agriculture engineering. A key solution for this challenge is to improve our water use efficiency in agriculture, to save water, and to produce more crop per drop. This will not only improve farm production and profitability, but will also reduce the environmental impact of agricultural production intensification. In fact, if you look at the past, the last 50 years, we see that food production intensification has resulted in major footprint, major impact on our water and land resources. In fact, the excess water resulting from the inefficient use of our water resources is the main vehicle of nutrient transport and contaminant transport to our groundwater and surface water bodies. So my work here at Biological Agriculture Engineering Department revolved around increasing the efficiency of agricultural water use, mainly through developing a new generation of sensors that allow us to track water movement in the environment, allow us to look on how water moves through the soil, plant, atmosphere continuum. An example of the technologies that we are working on is the use of fiber optics. With this technology, we can track water movement at very fine resolution along fiber optic installed in the ground. We can tell what soil water content at very high resolution. Agricultural and biological engineers have a key role in improving the use and management of our water resources through the design of water delivery and application systems that deliver water to the plant uniformly across the field at the right amount, at the right time, at the right duration. And also through developing irrigation management strategies that optimize our water use. If you want to make a difference in how water is managed currently, if you want to be in a place at the cutting edge of technology, this is the right place for you.
So an example of the cutting edge technologies that we are developing here is a set of sensing systems that will allow us to measure water content and movement through the environment. This is very important because that will allow us to identify the location where we need water to be applied or the locations that we need to be drained. So this sensor is based on fiber optic technology. We can measure temperature for thousands and thousands of kilometers using this cable. And we use it, we apply heat, and we use it to monitor saltwater content. We observe how heat dissipates from the cable, and that's what tells us what the saltwater content around it. If we have more saltwater content, the heat will dissipate fast. If we have a dry soil, the heat will dissipate less. So basically, that's what we have here is a two set of experiments that we are testing. One is to look at saltwater content measurement, and the other one is to look at the flux to measure how much water is flowing through in the soil.